Okay, this is the second question of our weekly discussion. And to summarize the problem, we have air inside a piston cylinder assembly, and it undergoes a cyclist process with three different states. Between the first and second states, as an isometric process, which is constant volume. Between the second and third states, it's an isothermic expansion, so it's constant temperature expansion. And between states 3 and 1, it's isobaric compression, which means constant pressure. So with these three conditions, the following diagram following diagram will be formed. And it might take trial and error, but this is the results that will check all the boxes that we had earlier. We're also given an initial condition and I guess some conditions for states 2 and 3. And yeah, that's the problem. I want to quickly talk about this R term. So, at least for air, this is the molar mass of air. For every mole, there's 28.97 pound mass associated with it. This can also be as work for grams per mole or kilograms per mole, but in this case, working in English units. And that's where this R of the line comes in. I don't think I fully explained this, but we recognize this value from chem. And these values, the two values underneath it, are just translations to different English units. The reason why the R of the line on top of it is important is because the line on top indicates we're working with moles. It indicates we're working with moles. So that's why the R of the line on top of it is referred to as the universal gas constant, because it's universally applicable to any gas. However, because each gas has its own molecular mass associated with it, as you see here, I start off with the ideal gas law. When I get this molar mass that comes out, the universal gas constant divided with the molar mass becomes the gas constant for that specific gas we're working with. That's the best way I can describe it. Anyways, returning to the ideal gas law real quick, I undergo this following derivation. I know that a mole can also be represented as the mass divided by the molar mass. That gets you the moles. And yeah, I do low convergence. Some low convergence stuff, like I move the mass over to the left-hand side. I move the universal gas constant above the molar mass. And I can simplify it to get this following equation, which is we'll be using a lot in thermodynamics. This is our version of the ideal gas law. Okay, with that all being said, we can finally start the problem. Okay, so I asked to find change in work as well as change in heat within the system, because it's undergoing a process, so something's going to happen. All right, so let's start with work first. We're very familiar with this, but our equation for work is integral within the cycle for pressure times change in volume. And I'm going to, once again, as I mentioned before, I'm going to break this up so that the dV is just m times d specific volume. So I can extract the mass out so that the change of work over mass is on one side. And now we just have the integral. And I'll also break the integral down into each respective processes. I wonder if the mic can pick up my voice. Okay. So we have that. What did I say earlier? I remember the first process. The first process is isometric, so I can instantly just ignore this, and I know this is 0. So I just have to solve for the next two states. Sorry, next two processes. And to get that, let's first figure out our bounds, because in our givens, we're given all the pressures. Given all the pressures. We're only given one temperature, but we'll do that later. We don't have any of the specific volumes, and we need that in order to do our integration. So we can get our value through, as I mentioned, the ideal gas law. So let me derive that into a form that we can use. At least for, we'll start here, because even though it's gone, let's just start there. We need it eventually. Okay, I have this. I have all the variables here. So technically, I need to solve for a specific volume right now. But I'm not going to, because I want to use this really cool trick. So basically, the idea is that because it's an isometric process, the specific volume at state 1 is the same as state 2. I can substitute these two equations with each other, and get some kind of relationship between the two. The same gas constant, so this will cancel out. I get the following relationship. I remember this from high school chemistry. It's like a really important law, and I remember taking a quiz on it and everything. So it's just really cool to see it show up again. I don't remember who exactly made this law, but I mean, I'll probably look it up later. But the whole point of this is we can then get our temperature at state 2. And it turns out it's just the ratio of the pressure between both state. So I get these numbers up here. I can plug in and get temperature at 2. Okay. That's our temperature at 2. Yeah, sure. We also know that during the process between states 2 and 3, it's isothermic. That is also temperature at state 3. So we have all of our pressure values. We have all of our temperature values. All we have left to do is get all of our specific volume values at each state. And we'll now use these equations up here. And I should have recorded after, maybe before I ate, but whoops. Okay. Remember, the R term is actually technically 2 parts. So we have the universal constant. Units are pound force per feet divided by pound moles, Rankins. And the molar mass of air is 28.797. It's pound mass per pound mole. What's the other part? Temperature over pressure. Okay. So state 1, this is our temperature, and it's 1 atmosphere, which is this. One thing I mentioned is we want to convert this from inches to feet, so let me just do it real quick. So I'll go on top. Okay, I think that's the right formula. I'll put a calculator and get my answer real quick. Okay, yeah, I get the right answer. 13.6. Oh, what's the units? Cubic feet per pound mass. Okay, and just to show that real quick, these masses cancel out. I guess these cancel out. So this feet squared will combine with this top one up here, become cubic feet. Temperatures cancel out. Pound mass can't. Oh, sorry, pound moles cancel out. So yeah, we're left with those units. Okay, perfect. Now let me get the other one real quick as well. That was a brain fart. Okay. I don't know why I solve this. Try to solve the same thing again. I want to solve for state 3 because isometric process makes it so these two are equal. Okay. Anyways, moving on. That's embarrassing. Okay, so that's what I actually wanted to solve for. Gotta make sure to edit that out. And then I can just change these values real quick. Just the temperature value. And remember from earlier, temperature only doubled. So therefore, the specific volume also just doubled. All right. So we have everything. We have all, for each state, we have pressure, temperature, specific volume. We can now solve for our work. Yeah. So it'll be 0 plus. Okay, let's talk about the process between state 2 and 3. It's an isothermic relationship. So it looks like, as I know, it looks like a curve. So there has to be some other way to integrate for it. We can't use like rectangle or triangle shapes or whatever. We have an equation though, the ideal gas law. So why don't we just substitute this in and see if we can get anywhere for that. Okay. And the last process is the isobaric. So therefore, we just pull, it's a pressure constant, we pull it out of the integral, da da da. Okay, remember, for this process, it's isothermic. Therefore, temperature is constant. And we know that the gas constant is, a constant, so we'll pull that out as well. Oh, and yeah, for this one, as I said, pressure is constant. Okay, let's integrate. Everything's great. Also, that's flipped. Whoopsie. All right. So this is our equation. And like I said, we have everything. So let's just plug it in and get an answer. R. What's R? Okay. Okay, and then, I guess let's put it down. It's fine. As you can notice, writing down your units is very important, so please remember that. Difference in volumes. Okay, I'll put in the calculator and get an answer real quick. Why are my answers matching? I don't remember why. Oh, no wonder. Let me put in a temperature real quick. I forgot about that. What's this? Between the process? Okay, so this is a T2 or T3 works. Okay, let me put in the missing piece and let me get an answer. Okay, I recognize this answer. I get 11,135 pound force per foot pound force foot per pound mass. 14.3 British thermal units per pound mass. So, I think I mentioned this earlier, but I guess that means we can raise 14 pounds of water 1 degree Fahrenheit, or raise 1 pound of water 14 degrees Fahrenheit, something like that. Yeah. Now now we can do the last part. Let's go back to the first law of thermodynamics. You'll probably, this is necessary to come back to if we want to do anything with work or heat transfer or thermal energy change of a system. All right, whatever. So, as I mentioned earlier, cyclic process means that your total change of energy of a system is zero, because where you start from is where you end. And I think in most cases, this term, at least for now, is referring to internal energy, because we end and start at the same temperature. That part will be consistent. So yes, it'll be zero. Okay, so we can confidently say that the heat loss or heat gain of a system is equal to the work that's done. And we have work from earlier, so let's just plug it in here. All right, so that's the answer from that you're expected to get from just doing the problem regularly during discussion. Wrong conjunction. I want to hop into a new topic real quick and mention these two important elements, because I don't think I have time to cover it next week. Now, hypothetically, what if I want to break down each process in this cycle and determine the change in work, change in internal energy, as well as change in heat transfer, heat loss, heat gain. So we can do it by using these values that we have for temperature and going to table A22. The 22 tables are ideal gas, kind of like approximations for air at different temperatures, as you see here, for things like enthalpy, internal energy, and this is, I think, entropy. For at least for now, that's what's relevant. So, given T1 is 540, we look on this table, this line, and we find our internal energy, which, at least for our, for now, we're going to assume that total change in energy of the system is just internal energy. And we also have another temperature here, 1080. And that is our total energy right there in terms of BTUs per pound mass. So let me just use those values. Let me just do some subtractions and get our change in internal energy. I believe we had an isothermic process between 2 and 3, so this is 0. Okay. So for process 1, 2, it's the temperature at 1080 minus temperature at 540. And I get, the difference gives me 94.89 BTUs per pound mass. And from the process that goes from state 3 to state 1, it's the reverse. Going from the internal energy at a state of 1080 degrees Rankins to a temperature of 540 degrees Rankins. All right, that checks out because, as we mentioned, change in internal energy. And that makes sense because the change in the total energy of the system should equal 0 when you sum everything up. And as you see here, summing it all up is 0, as we expected. What would not be the same is the heat transfer in the system. And that would be, using the first law, I should mention, we can easily get what the change in Q is. But I do feel like trash. I just add these two together and we're done. All right, I believe this all checks out. Yeah, okay. So, yeah, we want to break it down. Looking at each process, we can use table A22, get values for, internal energy based on the temperature, and, get our results. Okay, the last topic I want to cover for this problem is the compressibility chart, which will be taught within the following week. And what's really cool about it is that this is applicable to basically, I think, any gas. And about that, it's the ideal gas law. So I'm gonna show a quick example. So there's actually very little equations related to this. The first one is called the Z factor, shown right here. Next is and then the next three is just our reduced terms for like the three kind of standard variables or conditions that we derive usually from our work. Okay, so the idea is that, I'll show you a quick example. Let's take air, what we're working on. So air has a critical pressure and a critical temperature. So it's, So its critical pressure is 62 atmosphere. Its critical pressure is 37.2 atmosphere. Its critical temperature, 556 degrees Rankine. So let's take an example. Our example will be state 1 with these conditions as the initial conditions. Whoopsies, didn't catch that. Okay, so I'll plug in these values and we're gonna get our reduced pressure and reduced temperatures. Okay. So we've surpassed the critical temperature. So notice how we have a super low, this reduced pressure, which is like a ratio, is very, very low, and this reduced temperature is a very high, relatively high ratio. So with these two terms required, we can now return to our compressibility chart and track our location. First is the temperature, TR, reduced temperature. So it's along this, it's about 2.2, which I believe is along the dotted axis, 2.2, where would that be? Somewhere around like this line going back. Just to keep it simple, I'm gonna follow the 2 line. And our reduced pressure is super low, somewhere around here, right? So when these 2 lines converge, it's somewhere up here. So it's almost 1. So our Z factor, based on state 1, is almost 1. So what does that mean? Well, if we plug the 1 in this equation, we get the following equation. And I mean, it looks really simple, right? This is exactly what we had earlier, the ideal gas law. What this is saying is the ideal gas law is a very valid assumption because with a Z factor of 1, we return to our initial equation. To show a difference, I'm going to pick a pressure that's 1/2 of the critical pressure at a temperature that's the same as the critical temperature. And let's assume this is like a new state that this air is going to reach. So with these conditions being true, let's see our new reduced pressure and reduced temperature. So you get 1/2 for reduced pressure and 1 for reduced temperature. So our answer is going to lie within this axis as you follow this line right here. So follow this line back up. I come right here, I believe. Yeah. And this corresponds to a Z factor of about 0.82. So our Z factor is 0.82. This means that our ideal gas law equation is slightly modified to have this constant. So these changes kind of show that the ideal gas law is like kind of like a flawed assumption. This is only applicable at very, very low pressures and very, very high temperatures, which gives the gas its gas characteristics. So when these conditions are not true, our ideal gas law has to be modified in order to meet, reality has to be more realistic. And this table is a pretty important tool in a lot of engineering applications. So I just want to give a kind of like a quick introduction to this before Professor Altridge kind of gives a more in-depth analysis.